This lesson is part one out of section 12.5 called Mathematical Induction and Infinite Geometric Series. And that's not the purpose of part one at the moment. We're going to talk about converging and diverging as our first topic. We've been talking about geometric series where you take one term and divide it by the previous term, and that gives you R. With R, you can then determine whether this is a finite geometric series or an infinite geometric series. Here's two infinite series side by side. The first one you'll notice looks like the R is 1/2. 1/2 times 1/2 is 1/4. 1/4 times 1/2 is 1/8. R is 1/8. Something different here. What if I made a table of partial sums? That means the first term is 1/2, but the second term is the two added together. 1/2 plus 1/4 is 3/4. The third term is really the second term plus 1/8. If we added all these up together, got a common denominator, we get 7/8. And then the next term is 1/16, and if we add all these up, it's really easiest to take 7/8 plus 1/16. That'll give us a brand new total of 15/16. Now, as you look at these numbers, as they're getting larger and larger, you'll notice that they're not getting larger than 1. The second pattern, R sub n, is 1/32 plus 1/16. And this one, it looks like, is getting larger each time. So we're multiplying this times 2, which cancels and gives us 1/16. This times 2, and it gives us 1/8. And this times 2, and it gives us 1/4. So our R is 2. Look what happens when I start to add these together. Well, 1/32 plus 1/16 is, common denominator, 3/32. 3/32 plus 1/8, need a common denominator, is 7/32. 7/32 plus 1/4 is 15/32. 1/2 added in gives us 31/32, and then add in 1, and now we start to get a number that's getting larger and larger. This is, by the way, 1 and 31/32. So the sum is getting larger and larger and larger and larger. These numbers are getting larger and larger and larger because R is 2. Here's an example, a graph of the first one. And here is a graph of the second one. Now you'll notice here as the number n gets bigger and bigger and bigger, all of a sudden this graph starts to level out, it looks like, at 1. This graph, as n gets bigger, it looks like this is just getting bigger and bigger and bigger. The first one is an example of convergence, and the second one is an example of divergence. Convergence means it converges on a certain number. In this case, we can see it's a 1. Divergence means as it gets bigger in the x direction or the n direction, the y just keeps getting bigger and bigger and faster and goes up without a limit. So the first one, converging, has a limit, which is y equals 1. This all has to do with the common ratio. So let's try this again. Here's a brand new problem. The first number is 10, the second number is 1. If you notice, when you divide these, there's a pattern there. It's 1 divided by 10, 1/10. That's R. And that R is less than 1. And then if R is less than 1, we would say this series converges on a certain sum if it's less than 1. Here, when I do on B, R, which is 12 over 4 or 36 over 12, R is 3. Well, R is larger than 1. That 3 is larger than 1. So this series is said to diverge. Diverge means kind of to go off away from, whereas converge means to come to it. Let's do another one. 1 divided by 2/3 is 1 divided by 2/3. Reciprocate here, reciprocate 2/3 and make it 3/2. 1.5. Well, 1.5 is larger than 1. So that tells me that this particular pattern is going to get larger and larger, and that means it diverges. The second one, as I divide 16 by 32, I get 1/2. 1/2 is less than 1. R is less than 1. That means this series converges. So we went back to the first one. S sub n has an R of 1/2. And we're going to say any series that has a R that's less than 1 is an infinite geometric series, but it does have a sum. And this is a new formula for you. And we'll pick up on this on the next one. This one is called the infinite geometric sum. This is a brand new formula for you. Is the first term divided by 1 minus R. And with that, we'll stop, and I'll do part 2 on infinite series. That will come soon.